Welcome to my channel where we're looking at how to solve system of linear equations by Gaussian elimination. In our other video, we looked at reducing a matrix to echelon form, and so we'll be using that knowledge of reducing a matrix to echelon form to try and solve the system of linear equations by Gaussian elimination. So what is the procedure of how to solve a system by Gaussian elimination? So if you're given a system and you're asked to solve it by Gaussian elimination, the first thing you're supposed to do is to extract augmented matrix from that system. So extract the augmented matrix from that system of linear equations, and then after extracting the augmented matrix, reduce that augmented matrix to echelon form, and then solve by back substitution to get the solutions to the system. So I want to look at examples on how to solve a system by Gaussian elimination. So the first example is use Gaussian elimination to solve this system. So we are given 3a plus b minus c is equals to 1, a plus 4b minus 3c is 11, negative 2a plus 3b plus 5c is 21. So the first thing we do is to extract the augmented matrix. These coefficients, use this coefficient to form the matrix. So I can see 3, 2, negative 1, 3, 2, negative 1 is equals to 1. So instead of that, we just put this and then the 1 is there. This vertical line, then 1 is there. Then I can see the coefficient here 1, 4, negative 3, 1, 4, negative 3, and then 11. Then the coefficient here can see negative 2, 3, and 5. So negative 2, 3, and 5, and then 11. This matrix is what I call the augmented matrix. The augmented matrix. So this is the augmented matrix. Now with this matrix, we reduce this matrix to echelon form. So we have this leading entry here. We use this leading entry to create zeros below it in the column, first column. So to get a zero in this position, I take row 2, minus a third of row 1. So this will give me the new row 2. Then I also need a 0 in this position. So I'll take row 3 plus 2 out of 3 of row 1. So this will give me the new row 3. So just as we did while we were looking at reducing matrices to echelon form, once you have this leading entry here, you use it to create zeros in the positions below it. So these elementary row operations give us that zero, those zeros. So let's just do it for row 2. 1 minus a third of 3. That gives me 0. And then 4 minus a third of 2. This is like 2 over 3. So it is 4 minus 2 over 3. And that gave me 10 over 3. And then negative 3 minus a third of negative 1. And this is like negative 3 plus a third. What the LCM is 3. And this will be negative 9 plus 1. It's negative 8 over 3. That's what I have. I do the same for this 11 minus a third of 1. And that gave me 32 over 3. And then I come to this position and create a 0 here. And I've said to create a 0 here, I would have the entire row 3 plus 2 over 3 row 1. So in other words, negative 2 plus 2 over 3 of 3. That gives me 0 in this position. That gives me a 0 in that position. Now what about in this position? I have 3 plus 2 over 3 of 2. This is the same as 3 plus 4 over 3. Why the LCM is 3. And this will be 9 plus 4, which gives me 13 over 3. And that is why you're seeing this 13 over 3. What about in this position? I would have 5 plus 2 over 3 of negative 1. The LCM there is 3. And this will be 15 minus 2. And this is 13 over 3. I do the same for this position, and I get 65 over 3. Now, so I have this, I'm done with this first column. I now come to this second row, and I can see that my leading entry is this. So I want to use this leading entry to create a 0 in this position. How do I achieve that? To get a 0 in this position, I need, that position is in row 3. So I need this row 3 minus 13 out of 10 of row 2. 13 out of 10 of row 2. So what I mean is, this 13 out of 3, I would subtract from it 13 out of 10 of 10 over 3. Of 10 over 3. And this is 13 out of 3 minus 13 out of 3, which gives me 0. And then in this position, I have 13 over 3 minus 13 out of 10 of negative 8 over 3. Remember the negative and negative will be positive. So what I would then have, 2 will go here 5 times, and 2 go here 4 times. So the LCM there will be 15. And through going to 15 5 times, 5 times that will be 65. And minus plus, and this is 52. This is 52. So this will give me 117 out of 15. Now, so what I did this time, I had not simplified, but if I simplify this, you'll get 117, because 2 go here 1, and then is it 117? Yes, it's supposed to be 117. So 2 go here 1 into 3 1, and then 7. So it's 117 out of 15. Doing the same from this position, you will still get again 117 out of 15. But since I had not simplified, let me just leave them the way I had used them. They were 234 out of 30, 234 out of 30. But we've seen what we've done, that we want to use this leading one to create zeros below it. Then we shall have another leading one in this position, use it to create a zero below it. And once that is done, the matrix is in echelon form. So we have our matrix in echelon form here. Is that? This is our matrix in echelon form. Now, so we use it now to solve the system. And we write what we understand, the equations from that coming from the last matrix there. And the equations coming from the last matrix, remember it was A, B, C. So this was 3A, 2B minus C, and that's all you see. 3A plus 2B minus C equals to 1. This was the position of A. So what we have here is 10 over 3B minus 8 over 3C is equals to 2 over 3, and that's what we see. And finally, this was A, B. So what I have here is 234 over 30. C is equals to 234 over 30. So now we solve from this bottom part going up. Solving here, multiplying both sides by the reciprocal of 234 over 30 gives me C to be 1. So I find that C is 1. Then I move this other equation and substitute 1 wherever is C. What I would have would be 10 over 3B minus 8 over 3, remember C is 1, equals to 32 over 3. In other words, 10 over 3B equals, I take this other side, I would have 40 over 3. 40 over 3. Then multiply both sides by 3 over 10. That gives me B is equals to 40 over 3 times 3 over 10. And that means B will be 4. Now, so I have the value of C and I also have the value of B. I proceed with this other equation and substitute there B as 4 and substitute C as 1. Then make A the subject of the formula. A would be -2. Once I have my solutions, I have the value of C, A, C, and B. I write them in vector form, and that becomes the solution to the system. I write them in vector form. So I've written them in columns. So you may also want to write them in a row. You may want to write them as this, and there will be no problem. That will still be a solution to the system. So I want us to look at another example, how to solve a system of linear equations by Gaussian elimination. I have this system here. This is my system, and I want to solve it. So the first process, what we said, we extract the augmented matrix. So 2, -3, 1, 2, -3, 1, then 2, then 3, -4, 3, 7, 3, -4, 3, 7, then 2, 3, 2, 8, 2, 3, 2, 8, and reduce this matrix to echelon form. So we have this leading one, use it to create zeros below it. So what are our row operations? I would have row 2 minus 3 over 2 of row 1. That will give me a 0 in this position. And then in this position, I'll just take row 3 minus row 1. So let's cut out those row operations and see what we get. So 3 minus 3 over 2 of 2 gives me 0. -4 minus 3 over 2 of -3. This will be positive. So I'm talking of -4 plus 9. This is 2. 9 over 2. Where the LCM is 2, and this will be -8 plus 9, giving us a half. And you can see the half there. That's how I got it. And then I have this 3 minus 3 out of 2 of 1. And see, this will give us 6 minus 3 out of 2, which will be 3 out of 2. Doing the same to these two elements gives me 4 here. I now want a 0 in this position, and I said I would take row 3 minus row 1. So 2 minus 2 is 0. 3 minus 3 is 6. 2 minus 1 is 1. And 8 minus 2 is 6. Now I have this leading element here. I use it to create a 0 in this position. So what am I to do? For me to get a 0 in this position, if I was to use this element, then it will mean that I will take row 3 minus 12 of row 2. 12 of row 2. So what is 12 of 0? It will be 0. From this, I have a 0. 12 of a half is 6. From this 6, I have 0. 12 of 3 over 2 will be 18. 18 from this 1, I have -17. Then finally, 12 of 4 is 48. 48 from 6, I have -42. The matrix is in echelon form. The matrix is in echelon form. Now, since it's in echelon form, we now extract the equations from this last matrix and use those equations to solve by back substitution. So let's come up with the equations from the last matrix. And these are the equations I was able to extract. This is 2x minus 3y plus z equals to 2. That is our equation. These are half of y plus 3 over 2z is 4. And finally, -17z equals to -42. Now, so solving from the bottom going up, this last equation tells us that z is 42 over 17. Z is 42 over 17. Proceed with this other equation, and what we have is a half y equals to 4 minus 3 over 2z. But z is 42 over 17. So doing this gives us y as 10 over 17. Y becomes 10 over 17. And then you proceed this first equation, make x the subject, and substitute in the value of y and the value of z, and you get x to be 11 over 17. So we've solved that system that was given to us. Let's look at another example. And we are still using Gaussian elimination. So we have this system of linear equations. Very fast, we extract the augmented matrix. And you can see in this position we have no value of x. So I make it 0. But the rest are there. That are the coefficients of these unknowns. I have 1, 2, negative 1, negative 3. 1, 2, negative 1, negative 3. Then 0, 2, negative 2, 1. 0, 2, negative 2, 1. Then 1, negative 1, 2, 3. 1, negative 1, 2, 3. Very first, we reduce this matrix to echelon form. And so far, you know how to reduce these matrices to echelon form. When you do that, this is what you finally arrive at. This is the final matrix in echelon form. So this is an echelon form. Now, so we write what we understand by these equations, and I understand that since it was x, y, z, this would be 2, now x plus 2y minus z is negative 3, and this would be 2y minus 2z would be 1, and this would be 0, x plus 0, y plus 0, z is 7.5. It's this last equation that interests me, that x are that we can get values for x, y, and z such that when multiplied by 0, they give us an non-zero element or a non-zero number. This is not possible. It's not possible that we can have 0 times a number plus 0 times a number plus 0 times another number, and the result be non-zero. It's not possible. And so, since that is impossible, it means this system that we were given, the system that we were given above to solve, has no solution. And so that's why I wrote and said the last row of the last part implies 0x plus 0y plus 0z is 7.5, which is not possible. And therefore, the system that we were given has no solution. Or we can say the system is inconsistent. Inconsistent. This term we looked at it earlier when we began looking at solution of systems of linear equation. So far we've looked at an example where the system had a solution and an example where the system has no solution. So let's look at this other example and see whether the system has a solution or solutions or no solution. This is our system. So very first, we extract the augmented matrix, and this is the augmented matrix that I extracted out of our system. This is the augmented matrix. I want to very fast skip the other steps because you know to reduce to echelon form. We're just reducing this matrix to echelon form. This is the augmented matrix. And when I did that, this is what I got as my final result. So do it and see that you get that. I'm interested with this last row here. Look what the other two examples we looked at before we come to that. Look at this example. In this example, this was our last row. And it was very easy to see that negative 17z equal negative 42. That means the value of z could be obtained very fast. And therefore, the other values would also be obtained by back substitution. Then we came to this other example. And look at how the last row was. That we had 0 plus 0 plus 0, giving us a non-zero element. And we concluded and said that that is not possible, and therefore this system lacks solutions. Now let's come to our current example. And our current example, after reducing the system to echelon form, this is what we get. This is the echelon matrix. And look at the last row. Once I see the last row as 0, 0, 0 equals to 0, what this tells me is that this system has solutions. Not one solution, but it has infinitely many solutions. Because I have 0 plus 0 plus 0 plus 0 is equals to 0. So there are infinitely many solutions. Now, so how do we solve this? First thing, we extract what are the equations. Like I can see here, I have x minus 3y plus z equals to 2. And I have y plus 4z is 3. You can see that the leading element here is x, and the leading element here is y. And that z is not leading, is not a leading element. So the element that is not leading, we call it a free element or free variable. So in this case, z is a free variable. X and y are leading elements. Z is not, and therefore z is a free variable. So what we do in this case is that we solve the leading elements in terms of the free variables. We solve for the leading elements in terms of the free variables. And we can equate the free variables to some parameter, let me say t or s, where these ones represent any number, where t and s represent any number. So I've said that once I look at this shows that the above system has infinitely many solutions. So to solve this, we write the variables corresponding to the leading entries, the leading variables, in this case x and y, in terms of the other variables. And the other variables that are not leading, we call them the free variables. So in this solution, the leading variables are x and y, while z is a free variable. So what it means is that x should be solved in terms of z, and y should also be solved in terms of z. So I've said that we assign parameters to free variables. For example, we can let z be t, where t here will be 1, will be 2, 3, 4, and so on, or negative 10, and so on. Is there any number? And solve from the bottom going up. And so when we solve from the bottom going up, what we have, supposing that z is t. If z is t, what I would then have, this would mean that I have y is equals to 3z, is equals to 3 minus 4z, but z is t. Just a minute. But z is t, so y is 3 minus 4t. I can also solve x. From here, I can see that x equals 2 minus z minus plus 3y. 2 minus z plus 3y. But I know what z is, and I know what this is 2. So this is the same as 2 minus z. Z is t plus 3y. But y is 3 minus 40. What does this give us? This is 2 minus t, but this is 9 plus 9, and this is negative 12t. Negative 12t. This is plus. So what I have, this is 9 plus 2, which is 11, and then negative t, negative 12t will give us negative 13t. So that becomes our x. And that's what I have. Just a slight correction that this is z. Z was t. Y was 3 minus 4t. And x was 11 minus 13t. So this is our solution. Remember that this system has various solutions. If you make t to be 1, you get one set of solutions. If you make t be 3, you get another set of solutions. If you make t to be negative 100, you get another set of solutions. That's why I'm saying that this system has infinitely many solutions. And look at how it looked like, the bottom of that matrix in echelon form. This was the bottom of the matrix in echelon form. I want to look at one more example. And this is the example. Use Gaussian elimination, or using Gaussian elimination, find the general solution to the system below. Like the example we've had above, what we wrote was the general solution. And thus I said that if t is 1, then we would have one set of solutions. If t is 2, we'd have another set. So what we came up with was a general solution. So again, we require general solution from this. When we see, let's just extract the augmented matrix and then reduce to echelon form. When I did that, this was the augmented matrix, and then this was the echelon form of this. And then now extracting this is x1 plus 2x2 plus 3x3 plus x4 plus 2x5 plus 2x6 is equals to that. And that's what I have. And then I do the same for this to come up with this equation, the same to this, or this equation. Then lastly, I have this this is x5 minus x6 is equals to 4. Now what is interesting is the last row telling me that this system has infinitely many solutions. Is what it's telling me. And once I say this, I know that I'll be solving the leading variables in terms of the free variables. I'll be solving the leading variables in terms of the free variables. And I've said that in this example, I can see that x1, x2, x3, and x5 are leading variables, while x4 and x6 are free variables. So I'll assign the free variables parameters. So that's what I did. I assigned x4 to be s and x6 to be t. And so I began solving. So if you begin from this solving, x5 will be 4 minus plus x6, but x6 is t. So that's why you see that I say x5 is 4 plus t. 4 plus t is x5. But x6 is t. x6 is t. So x5 is that. x4 is s. What about x3? So just move here and make x3 subject of the formula. So x3 is -1 minus 5 over 4 x6, which is t, plus, no, it's minus 3 over 2 x5, which we now have. X5 was 4 minus not plus 2, that was x5. And then minus a half of x4. x4 is s. Doing that gives me, I did that and I found that x3 was -7 minus half s minus 11 over 40. I moved up and made x2 the subject because I already have x3, I have x4, I have x5, I have x6 equals to 0. Substitute x3, substitute x4, substitute x5, and substitute x6, and make x2 the subject. Doing that left me with x2 as 3 minus half s plus 3/4 t. And then I moved to the first equation and made x1 the subject. And remember that I've already found these other values. Substitute them here and make x1 the subject. And doing that gave me 9 plus 3s over 2 plus 11t over 4 as x1. And that is how we solve a system of linear equations by Gaussian elimination.